We show our visual analytics interface and its functionalities in this supplementary video. Our analysis interface has two tabs. The first tab that we see now is for interactively comparing and contrasting the fine-grained prediction uncertainty and error characteristics from two different deep uncertainty estimation techniques. In this work, we have primarily focused on the MC dropout and ensemble-based uncertainty estimation methods. The second tab that we see now allows comparative model sensitivity analysis for the same two uncertainty estimation methods. Now let us see the components of this analysis interface. Visualization results that we are analyzing here are generated from a deep convolutional neural network based generative model that, given an input viewpoint, predicts the corresponding volume rendered image of the data from that view. Based on the MC dropout and the ensemble method, we then estimate the pixel-wise uncertainty error and error variability images for each predicted image, and the results are shown in this interface for interactive analysis. The first component is a parallel coordinates plot that shows the input view angle parameters phi and theta and the estimated uncertainty and error quantities as individual axes for both the MC dropout and ensemble methods. The second component is a collection of heat maps that show view space uncertainty error and error variability plots for both MC dropout and ensemble methods. The purpose of this to be able to compare, contrast the uncertainty and error patterns produced by these two uncertainty estimation methods. The third component is the image panel on the right that shows the ground truth image, mean image, that is the expected image predicted from the model, and the corresponding pixel-wise uncertainty error and error variability images for detailed inspection. By hovering over on any resulting image, the corresponding polyline in the parallel coordinate is highlighted in red, and a pop-up window shows the corresponding error, uncertainty and error variability values. Our heat map plot allows lasso selection so that the subset of viewpoints can be selected where the uncertainty is either high or low. Since the heat map plots are all linked views, so selection on one heat map also highlights the selected region on the other heat maps as well. We can also see that a selection made on the heat map selects the corresponding viewpoints in the parallel coordinates plot as well, and the image view panel also gets updated with the selected views only. In this image view panel, we can sort the images based on MC dropout and ensemble method either in the ascending or descending order, either using the uncertainty values or using the error values or using the error standard deviation values. We can click on any of these images to investigate the view further and see more detailed uncertainty information. In this pop-up window, we are able to see the individual color channel wise uncertainty, error and error variability plots for this ensemble and MC dropout method. One observation here is that we see that the different channels have different uncertainty and error patterns. That means that the uncertainty methods influence the prediction of red, green and blue channels differently, and that is why the uncertainty and error patterns are different per channel, and users can select any particular view of interest and just click on the image panel, that will open up this pop-up window where users can investigate the patterns of red, green, blue channel wise uncertainty, as well as look at the combined uncertainty for that particular predicted image. The users can select a subset of views from the uncertainty heat map plot, and the corresponding images gets updated in the image panel, and the users can scroll through all the selected viewpoints to investigate the image, their corresponding uncertainty and error maps. Our interface also allows selecting different data sets for their analysis. For example, here we are switching from the combustion dataset to the velocity field of Isabelle dataset. We can see that the images and the corresponding heat map plots gets updated automatically. We can select now the asteroid impact dataset, the temperature field of it, and again the images and the heat map plots and the parallel coordinates plot gets updated automatically. Another feature our interface has is this channel selection drop down. Using this channel selection drop down, users can select either red channel or green channel or blue channel to see the uncertainty and error plots that are particularly generated from that particular color channel of the images. The users can also use the combined channel view, which shows the combined uncertainty, error and error variability plot. Our tool allows comparison and contrasting between any two uncertainty estimation methods as shown here. This model select option allows the users to select any two uncertainty estimation methods or results from any two uncertainty estimated models to show their results. For example, currently we are showing results from MC dropout and ensemble method. Now if we click this drop down, we can see that there is a third option that we have also tested in our interface, which is also an ensemble model that was trained differently compared to the one that we have selected now. So this ensemble 100% indicates that to generate the members of this particular experiment, we used the 100% training data and then we shuffled the data so that variability across different ensemble members are generated. For this ensemble 80% situation, here we have randomly selected 80% training data from the entire 100% training data for each individual member of the ensemble and then generated an ensemble. So we can see that we can, if we want to compare these results from these two ensemble models, then we can easily uncheck the MC dropout method and then select this ensemble 80, and then the interface correspondingly updates the results. Here we can see that we are showing the result of this ensemble, which corresponds to the ensemble 100% method and then the ensemble 80% method. Now again we can switch back to the previous state that we had. This shows the flexibility of our interface, and it shows that if we have other uncertainty estimation methods which are not ensemble or MC dropout based, our interface can also load results generated from such uncertainty estimation methods and allow interactive comparison and contrasting between them. We switch to the sensitivity analysis panel. Here we have two main components. The first component consists of the sensitivity and sensitivity variability heat map plots for both MC dropout and ensemble method, and on the right this component is the image view panel. Now the sensitivity values indicate that if the sensitivity is low, that means that if we change the input parameter value slightly from such low sensitivity regions, then the output images will change very little. But the high sensitive regions, if we select images from this region, that means that the output images will change very rapidly if the viewpoints are changed slightly. For example, this low colored region shows the low sensitive region for this combustion dataset. Let us select a subset of images from these low sensitivity regions, and on the image view panel we can see that the images that has the frontal view of the dataset is selected. So we can see that from these viewpoints, if we change the input view slightly, then the images will not change rapidly. But if we select a subset of view from the high sensitive regions, then we can see that in the image view panel, mostly the slanted and the side views of the images are selected. Now here, if we change the input view slightly, then that image will change very rapidly and it will sort of move towards the front view of the image, and that is why the sensitivity is high for such viewpoints. Here note that we also allow sorting the selected images based on their sensitivity values, either in ascending or in descending order. Let us discuss some of the findings and their implications that was made by analyzing these three data sets using our interface. The first observation is that the pattern of uncertainty for MC dropout and the ensemble method are similar, and the pattern for uncertainty and error heat map is also very similar for both the methods. This observation is consistent for all the other two data sets as well, as can be seen from here. This is for Hurricane Isabel dataset and this is for the asteroid impact dataset. We can see very similar uncertainty patterns and the error patterns are also highly correlated. Now this observation can be also seen from the parallel coordinates plot. Let's select high uncertain viewpoints from the Monte Carlo dropout based method. So this axis indicates the uncertainty values that was generated from Monte Carlo dropout or MC dropout method, and then this axis indicates the uncertainty generated from the ensemble method. We can see that the viewpoints that are highly uncertain with respect to the MC dropout, they are also highly uncertain in the ensemble method, and that means these viewpoints have high correlation between these two methods. Now if we just slide these selected viewpoints across the entire view space, we can see that this pattern is consistent across the entire view space. That means the high uncertainty predicted viewpoints from the MC dropout method are also having high uncertainty when they are estimated using the ensemble method. Another observation to make here is that if we look at the error values, so this axis indicates the error values generated from MC dropout method and this axis indicates the error value from the ensemble method. If we again slide, then we can see that the error values are also mostly positively correlated. That means when the uncertainty value is high, the error is also high, and when the uncertainty value is low, then the error value is also low. This observation is consistent across all the three variables. The implication of this observation is that in real life situation, when a model is used to predict an image of a viewpoint where the ground truth is not available, then we can still estimate the uncertainty values. And since we know that the uncertainty and the error values are strongly positively correlated by observing this tool, then we know that if we don't have the error values but we still have the uncertainty estimations, then looking at the uncertainty estimations, we can make an decision that whether the predicted image is trustable or not. Our next observation is made on the images that has been produced by this uncertainty aware models. So the observation here we have is that if we look at the uncertainty maps closely, then we see that the higher uncertain regions are essentially the regions where the sharp intensity values change happens, or where the data values are changing rapidly, that is the high gradient regions. The model essentially finds it difficult to predict pixel values for such locations. So the boundary regions and the convoluted regions inside the data has high uncertainty in their prediction. This is consistent across all the viewpoints and across all the data sets that we have seen. A very similar pattern also is seen in the error maps as well. We can see that the error maps also have very high erroneous pixel values that are on the boundary region and also the region where the sharp intensity value change happens. So this also shows a similar pattern that the model is making more erroneous predictions for such pixel values. Now this observation is again consistent in all the three datasets that we have tested. So this essentially shows a potential limitation of the underlying deep visualization model that we have studied in this work. This says that such deep visualization models have a scope of improving their accuracy by making them more accurate in predicting these high gradient regions, and then the results that will be obtained from such improved methods will have less uncertainty and less error. So our tool has also helped out in pointing out a limitation of the underlying models that has been studied in this work.